We're dealing with the knowledge area electricity and magnetism. The topic we're dealing with is parallel resistors. Right. Now, it would be disconcerting to have all lights go out each time a lamp burnt out. Now, for this reason, each lamp is on a separate circuit and is operated independently. So a parallel circuit is one in which two or more components are connected across two common points in the circuit to provide separate conducting paths to current. Reason being, like I've alluded to, if you have one bulb not working in your house, you don't want the entire house lights to be off. So you want to have independent circuits so that current can go through an independent circuit even if a bulb is burned. Right, now let's look at some rules related to parallel resistance. Right? There are essentially three. So the total current in a parallel circuit is equal to the sum of the currents in the separate branches. Right. The total circuit current is equal to the sum of the currents in the separate branches. And let's look at this. This is actually the law of conservation of charge. So this is actually a law of conservation of charge. Right, it may not seem like that, but it's essentially a statement of the law of conservation of charge. Now we know that if we have, let's say, we know and we've dealt with this, that I is equal to Q upon T, right? And which means that Q is equal to I times T, which indirectly means that if the time is constant when charge is passing through a particular point, Q is directly proportional to I. So which means if I have to now, let's just say we start with a battery and it's giving, so supplying 100 coulombs, it would mean that if we add the current in each of the branches, it will also have to be 100 coulombs. That's the law of conservation of charge. But let me illustrate it. So let's say, for instance, we have a particular battery here, and it's got a certain voltage. And we have, I'll draw a resistor like that, and here we have that resistor, right? And then we can have another resistor here connected in parallel, say those 2 points, and then we have another resistor, right? So we have the resistors in parallel. But let me just draw this a bit neater. So you have right, 3 resistors in parallel. So let's say, for instance, this resistor is R1, let's call that R2, and let's call that R3, right? If we look at this, and we know that conventional current travels from the positive to the negative, so it travels, and as it travels, it branches out. It branches out and goes through the respective resistances. So let's say, for instance, if we have a current here, and that current is, say, I, total current. When it comes to the resistor, you see that you have I1 there, and some go in there. So let's say there's I2 and some coming through here. So what we're saying is, if current in the circuit is moving from the positive terminal, it comes to these branches and it splits. As it splits, you will see I1 going through resistor 1, R2 going through resistor 2, and R3 going through resistor 3. So the total current passing through the branches will be equal to the circuit current. And as it leaves there, again, we got our I total, and then it goes back to the battery. So in terms of charge, it's the law of conservation of charge, and that essentially is saying the charge is moving in this particular circuit, they constant, right? In the external circuit, they are constant. So if we now look at the potential difference across all branches of the parallel circuit, they have the same magnitude. So let's go back here, and if we look at this, and let's say, for instance, this particular battery has a voltage of 12 volts, right? Say it has a voltage of 12 volts. What we're saying is, so across here, if we put a voltmeter here, it will measure 12 volts, right? That means resistor 1, resistor 2, and resistor 3, since they are connected across common points, the voltage across each and every resistor there will be the same, right? The voltage will be the same. The voltage will be the same in that parallel branch. But what happens, the voltage is the same across the parallel branch, which is 12 volts, and the battery is 12 volts, so 12 volts is across those parallel resistor. But the circuit current is subdivided, but the total sum in the branches is equal to the sum is equal to the circuit current, right? And how much current goes into each branch depends on what the resistances in that particular branch are. if they all equal resistances, then we would expect that the current to divide equally among the resistance. Right, now, here we said the potential difference across all branches of a parallel circuit must have the same magnitude, right? So yes, they have the same magnitude, which means that in this case, V1, right, across resistor 1 is equal to this V2, which is the voltage across resistor 2, and V3 is the voltage across resistor 3. Right, so these voltages are all equal because in a parallel branch we find that the voltage is the same across all the resistors. Unlike a series circuit, right? There we found that the voltage of the battery is divided or proportionately divided across resistors. Right, now this here is essentially a law or conservation of energy. Right, it may not look like that, but it is. We know that voltage is what? Voltage is actually equal to potential difference, right? And potential difference, well, it gives us what? An indication of the potential energy difference. Right, it gives us an indication of the potential energy difference between the terminals of a battery, right? And that means what happens is that it gives us an indication of thus it does then gives us an indication of the amount of work that a battery can do, which right, it then could just say gives us an indication of the amount of work a battery can do. That's it. So it's essentially a law of conservation of energy. We talk about the voltage of the battery, but voltage is essentially the potential difference between the positive and negative terminal of a battery. But as we have alluded to in a previous lesson, that the potential difference gives you an indication of the difference in potential energy between between the positive and the negative terminals of the battery, right? And if we know the potential energy difference between the two, we know what the capability of we know that the battery can do work, and the change in potential energy of the battery is an indicative measure of the amount of work that the battery can do. Right, and then we have the third rule, which is the reciprocal of the equivalent resistance. That's the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the separate resistances. Right, so essentially what we're saying, 1 upon R total is equal to 1 upon R 1 upon R1 plus 1 upon R2 plus 1 upon R3, right? Sometimes we write it as, instead of 1 upon R, sometimes we may even write it as 1 upon REQ, which means equivalent resistance, and then we say it's equal to 1 upon R1 plus 1 upon R2, like that. And we can continue with it, right? And sometimes we also say 1 upon R parallel, right? So it's a different way of writing it, but it's still, the relationship still holds for resistors in a parallel branch. So this is one way of writing it. But if we have only two resistors, here it can be written as R total is equal to R1 times R2 plus over R1 plus R2, which means it is a product over the sum. Right, so that is a relationship that we get if we make R total here the subject, R total the subject of the formula, instead of just 1 upon R total. But maybe let me just illustrate how that works. So if I say 1 upon R total is equal to 1 upon R1 plus 1 upon R2. We know if we do this, then we say if my LCM is R1, R2, then R1 goes into R1, 2, I'm left with R2, plus R2 goes into there, we have R1, right? Which means 1 upon R total. Okay? I'll just put T there. Now, what happens here, if I want to now say multiply the left hand side by R total, and you know this is an equation, so we want to be fair. What we do on the left hand side, we must do on the right hand side. I've got it there. So now we know R total, and that would cancel out, and that would give us 1. 1 is equal to R2 plus R1 upon R2 R. Let me just do that properly here. It's equal to R1 R2, right? Okay, times RT, but I'll write RT a bit further away. What I'm going to do is multiply this by R1 times R2 R2, right, and we know there's RT, and okay, we know there's RT, and this is R2 plus R1. So, like we said, we need to be fair what we do on the right hand side, so I have to multiply this side by R1 times R2, right, divided by R2 plus R1 or R1 plus R2. So we know that and that cancels out. So what I'm balanced with is R total. And what's R total? This whole thing multiplied by 1 is R2, R1 times R2. Okay. Okay, I'll just switch that, which means R1 plus R2. So if you are given only two resistors in a circuit, you could use this formula. It's an easier way to work out the problem. So let's say, for instance, I have a circuit here, right? And I have a resistor, let's say a resistor here, and let's say that resistor is 1 ohm, and I have another resistor here, and let's say it's 9 ohms. I've chosen that so that we can I can illustrate this quickly. So, and let's call that R1, and let's call this R2. If I want the total resistance of this, all I need to say is that R total is equal to R1 times R2 upon R1 plus R2, which would mean if I say 1 ohm times 9 ohms upon 1 ohm plus 9 ohms, which means is so it's 9 ohms upon 10 ohms, right? So it's 9 ohms divided by 10 ohms, which is then equal to 9 ohms is the equivalent resistor, which means if you have these two resistors in parallel and you substitute it for one resistor, the equivalent of those two parallel resistors is one resistor that has an a resistance of 0.9 ohms. Now we could do it this way, or I could have alternatively done it this way. I could have said 1 upon RT is equal to 1 upon R1 plus 1 upon R2, which would mean 1 upon 1 ohm plus 1 upon 9 ohms. Right? And then I would say 9 ohms is my LCM. It would mean 9 ohms. Okay? 9 ohms plus 1 ohm, which would then be 1 upon RT is equal to 10 is equal to 10 upon 9 ohms. R total, therefore R total is equal to 9 upon 10 ohms, which is 0.9 ohms. You can do it either way, but I prefer this one because it has, we have derived that particular equation from that one, and it's easier. You just take the product of the two, divide it by the sum, and you get your resistance. Right, now let's look at this one here. Diagram showing resistors connected in parallel. Okay, we have this. So essentially resistors in parallel. Okay, the first one is not in parallel, it's just one resistor, but I'll just illustrate what I want to give you an indication of what the voltage is across that particular resistor. So here we have a voltage of the battery which is 12 volts. Okay, that's fine. Now it says determine the voltage across 1, 2, and 3 resistors, and I'll show you this successively, but they in respective circuits, right? Each resistor has a resistance of 2 ohms. Alright, so here you've got this particular resistor. It's represented like this. Like I said, I normally like to represent them like that, but here we've got this resistor and it's got a resistance of 2 ohms. Okay, so what the voltage across this particular battery is connected across those 2 points, and the resistor across the voltage across this resistor is the voltage of that particular cell, which means it's 12 volts. Right? There's the voltage across that resistor. If I had another resistor here, let's say instead of 2 ohms, I had this resistor was 10 ohms, or whether this resistor was 20 ohms, or whether this resistor was 40 ohms, right? The voltage across the resistor would still be 12 volts, because that's the voltage across, of that particular battery. So when the resistor is connected across the battery, the voltage that the resistor has is the same as the voltage of that battery, right? And if we now want to work out what the current in this particular circuit is, we say, okay, I total, we could say, is equal to V total upon R total. Okay? And here V total is actually the voltage of the cell, which is 12 volts, divided by 2 ohms. It means the current in this circuit is 6 amps. That means if I put an emitter there, or anywhere in the circuit, there, or there, or there, right, wherever you put the emitter, and you know an emitter measures current, it's going to show 6 amps here, 6 amps there, 6 amps everywhere like that. Okay, it's going to show you 6 amps, which means we know if we're dealing with conventional current moves from the positive, so it goes through the entire circuit. There's one conducting path, and the current in the circuit is 6 amps, right? Okay, let's look at the next one. We're dealing again, still it was 12 volts, and here it's 2 ohms, and that's 2 ohms, and let's say this is R1, and let's call that R2. Right. Now, here we've got our resistors in parallel and they connected across 2 points, two resistors, and these 2 points that is connected across is connected to your battery, as you can see, right? It's connected to your battery. Okay? Now, what we want to know is what is the total resistance here. We want to know what's the total resistance. So if we want to calculate the total resistance, we can say 1 upon R total is equal to 1 upon R1 plus 1 upon R2, which would then mean 1 upon 2 ohms plus 1 upon 2 ohms, which is 1 ohm, right? But that's 1 upon R total is 1 ohm, and the reciprocal of that R total is still 1 ohm. Like that. Had I used the formula that I said R total is equal to the product of the divided by the sum, it would still be 1 ohm. Okay? So that is the total resistance. That means if I substitute this resistor and that resistor and I want an equivalent resistance for the two that are in parallel, I could then replace them by one particular resistor and it can be connected in series in this particular circuit. But now, if we want to know the current in the circuit, which would mean I total is equal to V total upon R total, okay? But what is my V across this branch here is going to be 12 volts, because that is your voltage of your battery. Okay, so that is 12 volts, 12 volts upon the total resistance for that is 1 ohm, and therefore the current in this particular circuit is 12 amps, right? So you have two resistors, and but these two resistors aren't connected in series, they connected in parallel. See what has happened to your current in a circuit. The current in the circuit has increased, and it's actually 12 amps. Right. See there we had 6 amps when we had one resistor. Here I've put resistors in parallel, so the current in the circuit is 12 amps, which means that the battery is now supplying more current than when we had a single resistor like this. So now it's supplying 12 amps. Right, let's go to one more. Now we still have a 12 volt battery here, but this time you got three resistors in parallel: R1, R2, R3, and each one is 2 ohms. That's 2 ohm, that's 2 ohms, 2 ohms, and that's 2 ohms. If we want to know the total here, I haven't derived a formula for 3 resistors in parallel, so we use R1 upon R total is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, which means here we have, right, 1 upon 2 ohms plus 1 upon 2 2 ohms plus 1 upon 2 ohms. And we say, okay, LCM is 2 ohms, which means in this case, 2 goes into that 1, so it's 1 ohm plus 1, right? Ohm plus 1 ohm. Okay, which means we've got now is 3 upon 2 ohms. That is, we have 1 upon RT, right? So maybe here I've got both in ohms. I may just need to take that out. Yeah, so let's just take that. Sorry about that. Take that out. Right, it give me 3 upon 2 ohms, and RT is equal to 2 upon 3 ohms. That is my total resistance. Right, for that particular circuit. Now if I want to know I say okay, it means VT is the total voltage, and there's the voltage of my battery, right? It's supplying this voltage, and we have R total, right? Which means in this case here now it's still 12 volts, okay, and divided by 2 upon 3 ohms, which then gives us 12, right? Okay, so which becomes times 3 upon 2, right? Right, and that gives us, so that's volts, and that's ohms, which then gives us 18 amps. See, here you've connected one more resistor in parallel and see what happens to the current. The current that the battery supplies is 18 amps. It means the battery is working much harder because it's giving supplying more current to the external circuit. Right. So I mean, having resistances in parallel or bulbs in parallel, it uses much more current, right? But it has the other advantage that, each bulb has its own conducting path. So if you switch one bulb off, the whole house bulbs don't go off like that. Okay, let's look at the next one. Here we say what is the voltage across a single resistor circuit that has a voltage of 2 volts. Right, so this is it's obvious in a sense. So let's say this is 2 volts, and we know if I've got a battery, if I've got a resistor here, doesn't matter what the resistance is. As you can see, the question hasn't given us what the resistance is of this particular resistor. It could be 10 ohms, it could be 20 ohms, it could be 1,000 ohms. Right, what we do know that the voltage across this particular resistor will be equal to the voltage that the battery is providing, so it will be 2 volts. Right, so whether it's a 10 ohm resistor or a 20 ohm or a 1000 ohm resistor, the voltage across would be 2 ohms. 2 volts. What would be different, obviously, is a current in that in this particular circuit. If your ohms is very high, the current in the circuit will be low. Since it's the circuit current and the resistance and the voltage is related by the equation I is equal to V upon R. Right, now if we look at the next one, you have a 2 volt battery again, and you got resistor R1 and R2 of 1 ohm each, right, in series. So here they're in series. Okay, so we have at each 1 ohm each in series. Okay, let me just check this quickly. Yeah, right, 1 ohm each in series. So that means this is 1 ohm and that one is 1 ohm, right? So you got 1 ohm, and now the question says calculate the total resistance. So we know that the total resistance here in this case, and what is our battery, it's 2 volts. 2 volts, right? So what is our total resistance? It's going to be R total. Remember, this is one conducting path. It means it goes like that, like that. The current doesn't split and it goes. So these two resistors are in series, which is equal to R1 plus R2. That would be 1 ohm plus 1 ohm. So the total resistance is 2 ohms. Now, if you want to know what is the circuit current, and the circuit current would be, we want the circuit current, which means it's I total is equal to V total upon R total, right? Means we take the total voltage as well as the total resistance. And total voltage is 2 volts. Total ohm resistance is 2 ohms. So the total current is 1 amp. If I put my ammeter there, or there, or there, or there, all going to be reading 1 amp. It's going to be 1 amp like that. And there's going to be 1 amp. And there's going to be 1 amp, right? Because the circuit or the resistors are connected in series, and in a series circuit like this here, the current is the same everywhere, right? And if we want to know then what is the voltage across each resistor, if I put a voltmeter here like that, and I put a voltmeter here like that, right, what would the voltages read? We know that when we have resistors in series, they are potential dividers. Unlike a parallel circuit, here you got 2 volts, and wherever you have a resistor, there's going to be a potential drop. So at this resistor, you're going to have 1 volt, and at this resistor, you're going to have 1 volt because they're equal resistances. If they weren't equal, we'll need to calculate what the voltages are, and the voltages are dropped proportionately depending on the size of the resistor. So here we see 1 volt plus 1 volt give us a voltage of the particular resistor, which means here calculate the voltage across each resistor. So each resistor would have a voltage of, so to say that's 1A, that would be A there, that is B, and C would be 1 volt, right, 1 volt across each resistor, correct? Right, now if we look at the next one, here we have three resistors, right? Okay, R1, R2 and R3, and they all in series. The voltage of the battery is 7 volts, so the voltage here is 7 volts. What is the voltage across R3? So let's call this R1, let's call this R2, and let's call this R3. So we want to know what is the voltage across R3, right? If the voltage across R1 and R2 is 1 volts and 4 volts respectively. So here, if we have a voltmeter there and there, we're saying this, the voltage is 1 volt, and across this one and this one, the voltage is 4 volts, right? So if we put a voltmeter here, what would this voltmeter measure? Right? We want to know that, but we know that this is 7 volts. And what do we know? That when resistors are connected in series, they are potential dividers. What? They divide that particular potential. The potential of what? The potential of the battery is divided among those resistors. And it's divided in a way that is proportionate to the magnitude of the resistance. So here in this case, we know that we've got V of battery, or V total, is equal to V1 for resistor 1 plus V2 resistor 2 plus V3 the voltage across resistor 3. But we know the voltage of the battery is 7. V1 we know is 1 volt. V2 we know is 4 volts, right? V2 is 4 volts plus V3, we have to find it out. So V3 is equal to 7 volts equal to 7 volts minus 5 volts, right? And that is V3, so therefore V3 is equal to 2 volts, right? And so there we have that. Right, now let's look at the next one. Here we consider a circuit with two resistors connected in series, right? Two resistors, there's two resistors, and they're connected in series. And then there's three resistors, and they connected in parallel. Right, so, and the voltage of the battery is 7 volts. So let's look at this one. We have that. One resistor, two resistors, and then we got one, and we have two, and we have three resistors like that, correct? And then here we have, this is 7 volts, and let's call this R1, let's call it R2, Right, we could, if you want to, R3, R4 and R5. We didn't need to at this stage, but I've just labeled them like that. Now here it says, consider this, right, the voltage of the battery is 7 volts. What is the voltage across the parallel resistor combination? If the circuit, in the circuit shown, the voltage across the series resistors is 4 volts and 1 volt respectively, right? So we have, it's 4 volts and 1 volt respectively. So here it is 4 volts, whichever one, right, 4 volts and 1 volt respectively. So in total we got 5 volts. But we know the battery has a voltage of 7 volts. So we know that here across this branch we will have to have 2 volts. Right? So once you know what the voltage across the parallel branch is 2 volts, what we can then say is that the voltage across R3, R4 and R5 will be 2 volts, right, because they form part of a parallel branch. Now let's look at the next one. Here you got two resistors, each of 2 ohms each, right, and they are connected in series across a 10 volt battery. What is the total resistance? Okay, this is a fairly easy one now, which means 10 volts, and which means, let's just do it properly. So here we have that, and we got 2 resistors there, okay, and current going that way. So let's say this is 2 ohms and that's 2 ohms, and we want to know what is the total resistance. So this is an easy one, which is R total is equal to R1. Say if I call it R1 and I call it R2 plus R2, which would mean 2 ohms plus 2 ohms is equal to 4 ohms. Which essentially means if I really had to now do this, I could have one particular resistance here of 4 ohms, and it has the same voltage. That means I could have then reduced those 2 ohms, the 2 resistors of 2 ohms each, and have 1. So this is like an equivalent circuit to this one here, right, in the sense that it has the same resistances. Right, now let's look at the next one. Here we got that which says 2 resistors, 3 ohms and 7 ohms are connected in series across a 21 volt battery. So there we have, and let's say this is a 21 volt battery, and here I have a 3 ohm, right, 3 ohm resistor and a 7 ohm resistor. Okay, so what is the total resistance? The total resistance R total would be, let's call this R1, let's call that R2. Total resistance would be R1 plus R2, right, which is equal to 3 ohms, which is equal to 3 ohms plus 7 ohms, which is 10 ohms. Okay, and it says what is the current in the circuit? The current in the circuit would be I total okay, is V total upon R total, which means 21 volts upon 10 ohms. So the current in the circuit is 2,1 amps. Right, 2,1 amps. But now it says what is the voltage across the 3 ohm and 7 ohm resistor. We know collectively the resistance across the 3 ohm and the 7 ohm collectively is 21 volts. And what do we know is that the current in the circuit there is equal to 2.1 amps. Right, now if we want to know the voltage across, say, the 3 ohm, so the voltage across the 3 ohm would be V across the 3 ohm, right, is equal to I, current in the 3 ohm resistor, times the resistance of the 3 ohm resistor. So what is the current in the 3 ohm resistor? The current in the 3 ohm resistor, if we're concentrating on that and all the information related to that 3 ohm resistor, we know the current through that is the circuit current, which is 2,1 amps. Times, we're dealing with a 3 ohm resistor, so it's 3 ohms, which means that the voltage across it is 6.3 volts. Right, so if we put a voltmeter there, it's going to reach 6.3 volts. Now we want to know how much is it for the 7 ohms. We know that 6.3 plus whatever drops on the 7 the voltage that drops across the 7 ohms must give us 21 volts. So which means it's equal to I of the 7 ohms times R across the 7 ohm resistor. The resistance of the 7 ohm resistor, which would then mean the current is the same, 2.1 amps, right, times 7 ohm resistor, isn't right, which then is equal to 14.7 volts. Right, so there you have it. But there you have that, and there you have that, and if you have it like that, together they give us 21 volts, which is the voltage of the battery. Right, now let's go and have a Phet demonstration. Right, now I'm gonna construct this circuit. It gives you an illustration of what happens when we gonna have resistors in parallel, what happens to the current, and what's the voltage across the parallel branch. So let's say, for instance, I now have a battery here, right, and I'm connecting a copper wire, right, and I'm connecting a copper wire there. So let's say I have that, and I'm going to connect a switch, okay, and here we have a bulb. Alright, maybe let's do that, and I connect there. I have that, okay, and there we have this. Alright, okay, there I've got a battery, a bulb, and a switch. Okay, now let's say, for instance, I now close this particular switch, right? And then we have current flowing through the circuit. But let's say if I want to know the voltage, see what's the voltage of this battery, and the voltage of that battery, the voltage is 9 volts, right? Which is fine. But now I want to know what's the voltage across my resistor, so I can put it here and I can put it there, and what do you see? It's 9 volts, right? Now here it's showing electron current. If I change it here, then that shows conventional current, right? Moving from the positive to the negative of the circuit, right? Moving from the positive terminal to the negative terminal of the battery. Right, and if I want to know what's the current in here, I say, okay, I put my ammeter there, it says 0.9 amps, which is fine, right? But obviously we'll need to be able to calculate that. So if I had my value there, you can see it's 9 volts, which is my battery, and the ohms or the resistance of my bulb is 10 ohms. So we know that 9 divided by 10 is 0.9 amps. I can put this ammeter there. What does it read? It reads the same thing because it's a series circuit. I put it there. What does it read? 0.9 amps. So wherever in a series circuit, it reads 0.9 amps. Okay, now what I'm going to do is I'm going to put another resistor in parallel. So here we go. I'm opening the switch. So I'm opening the switch, get one more, put another switch, and then we put the bulb there. Let's do that, and let's do that here, and let's do that. Right, now I've got two resistors in parallel, right, and across the battery. So say right, I've got my voltage here. So now see, this was the advantage of a parallel circuit. Let's consider it to be one room there, and the other room is not, the switch hasn't been closed, so we got current in one complete circuit there. If I do that, then both, right? If I decide to open that switch, I still got the bulb burning in the other room, so to say, right? In that other circuit. And what do I want to do? If I look at my voltages of my battery, surely you know what the voltage is. The voltage will be 9 volts, right? And we are assuming obviously that the voltage that we're measuring here is the potential difference, and we're assuming that there's no internal resistance in the battery, right? Okay, so in this case, we just the voltage of the battery is what we're reading on this voltmeter, right? So we're happy with that. If we take the voltage across this resistor, let's say close it, and we find 9 volts. If I take it across this resistor, it's 9 volts. And like I said earlier, that I mean the voltages or the voltages across parallel resistors is the same. But now let's look at the current. What is the current in the circuit? That the ammeter says the current in the circuit is 1.80 amps, right? And then what is the current in the branch? It's 0.9 amps. What's the current in this branch here? Is 0.9 amps. So 0.9 plus 0.9 give us 1.8, which is a circuit current which we measure there, or we could measure there. But here is the current in the branch, right? So that would be the current in the branch. Right, now let's go and have 3 resistors in parallel. So I have one more now. Here, let's close the open that. Okay, have another switch, have another bulb. Okay, you have another bulb here, and right now if we look at this here, about there we find I can close the switch, the other 2 switches are open, no bulb, the bulb doesn't light. Now I've got all 3 switches closed, right? What do I want to do again? I want to measure the voltage, okay? If I measure the voltage across all these resistors here, what does it show? It still shows 9 volts, right? If I measure it across there, it's 9 volts. If I measure it across here, it's 9 volts, right? So it's 9 volts. So if we have resistors in a parallel branch, the resistors in a parallel branch all have the same voltage, right? So when we have a parallel branch, we consider the voltages across the parallel branch to be the same, but when we have a parallel circuit, we consider the circuit to be a current divider. Unlike a series circuit is a potential divider and the current is the same throughout the circuit. Here, when you have resistors in parallel, the voltages across the resistance is the same, but the current is different. So let's see what is the current in this particular um, circuit. Remember the last one, it was 1.8, right? And let's look at this. Whoa, there we see is 2.7. The more resistors you have connected in parallel, the circuit current increases, right? The circuit current increases. So what is in each one here now? Each one is 0.9. What is that? Also 0.9. Since the resistors have equal magnitude, you can see that the filament or that bulb has a resistance of 10 ohms. Each bulb has a resistance of 10 ohms. And if I do this, it's also 9. So 9 in 3, which is the total of 2.7, which concurs with our sorry about that, which concurs with our circuit current. Right, now if I have this, now let's do this. What I'm going to do is I'm going to change the voltage slightly of this battery, right? Here, I'm going to change the voltage. Now see, when I change the voltage, what happens to my current in the circuit. See, I've changed the battery voltage to 16.50 volts. What has happened to the current in each of the branch? It's 4.9. It would be 1.6, 1.65, 1.65, 1.65, right? It divides. So that would be the current in the circuit. By changing the voltage of the battery, I have increased it The current in the circuit increased, and then the current in the branches increased, but because we've got equal resistances, um, they then had equal amps passing through them, right, which is 1.65. Now let's say if, for instance, we have this, and I'm going back now here, and I'm taking it back to but let me perhaps just show you this. I'm increasing the voltage more and more and more of my volts. See what happens. Right. As I increase more and more, can you see what's happening at the battery? That battery is working, very, very hard. You can see it's virtually going to be burning out, right? And because of the voltage that's being dropped across these particular resistors, so it means the battery is working hard. It's doing a lot of work, and we find that it's losing its potential energy significantly. And once it loses its potential energy, then we need to replenish that potential energy. That means more chemical reactions have to take place in the battery to increase the potential energy of that battery. Right. So let's say if I'm now going back, right, back to 9 volts. So there we have it. Now let's do something else, and let's say, for instance, I want to now change the resistance of one battery, of one bulb. So we know our bulbs have a resistance of 10 ohms, but I'm going to change one and see what happens to the current, right? This time we don't expect the current to be equally divided in all the resistors. They only equally divided if all the resistance are equal. But now I'm changing the middle resistance. See what happens now. Right, I've changed that resistance to 26.5 ohms, right? Or let's just make it maybe 20 ohms. I'll just double it. Right, so yeah, so even if you're doing a mental calculation, you can quickly see what's happening. So see what your current in that bulb, it's 0.9. What's it here? 3.45. Double the resistance at current halved. And here I've done that, and what's it? 0.9. Right. So it's 0.9, right? Plus 0.9, 1.8, plus it's 0.45. What does it give us? In total, it gives us 2.25. That's the circuit current. Right, and if I now change this, and I could make it into symbols. So there we have the thing, right, the current moving. Right, and if I want to change this just to show you electron current would be the other way. Right, but we're using only conventional current. Okay. Right, now let's consolidate what we did in the demonstration. Right, here I have screenshots of that demonstration. So let's have a look. In this parallel branch, our equivalent resistance is equal to, let's call this R1, R2 and R3, which means 1 upon R1 plus 1 upon R2 plus 1 upon R3, which will then be equal to 1 upon 10 ohms plus 1 upon 10 ohms plus 1 upon 10 ohms, which would mean 10 ohms, which gives us 1 plus 1 plus 1, which is 3 upon 10 ohms for 1 upon Rp, and therefore Rp is equal to 10 upon 3 ohms. Okay, I'll just leave it in this form. Now if we want to know what's the current in the circuit, we say I total is equal to V total upon R across the parallel branch, right? But which is would be equal to R total, okay? And that is equal to 9 volts divided by 9 volts divided by 10 upon 3 ohms equal to 9 volts upon 10 upon 3 ohms, which is the same as 9 volts, right, times 3 upon 10 ohms, which gives us 2 2.7 amps. And as you can see, that is what we have here, right? That gives us an indication that that's the circuit current. So if we look at this, the circuit current is 2.7 amps, whether that ammeter was placed here or whether it's placed there, right? The circuit current is 2.7 amps. But here we now have 3 equal resistance, right? All of 10 ohms each. So we know that the current in the branches must equal to the current in the circuit, right? So if we now look at this, I've illustrated here, we have got that in that 10 ohm resistor we got 0.9 amps, right, which is the current in R1, right? If we now look at the next one, we find that there again it's 0.9 amps, right? So in each one, like I said, here, this just illustrates it, that is 9 amps. And since you have 9 amps in each, which gives us a total of 2.7 amps, and the 2.7 amps is essentially our circuit current. Is essentially our circuit current as indicated here. Okay. All right. Now, if we look at this here, here we have a 9-volt battery, and when we started off we had only a 10 ohm resistor, and the circuit current was 9 amps. And then we continued adding resistors in parallel, and as we added resistors in parallel, what did we see? We saw that the circuit current increases. Right, so here you have it, and we will carry on in the next lesson.